Here's one of the most famous laws in all of astronomy. Square the time a planet takes to orbit, and it's proportional to the cube of its distance from the Sun. Kepler spent years staring at data to find it. But watch, we're going to pull it out of thin air. No orbits, no calculus. Just by asking what units the answer could possibly have. So here's the picture. Two bodies held together by gravity, swinging around each other on circular paths. What sets the rhythm of that dance, the period, the time for one full turn? Let's find out using nothing but dimensions. Let's write down everyone who could matter. There's the period of rotation, which we'll call t. The mass of the first body, and the mass of the second, call them u1 and u2. And the distance between them, r. That feels like the whole cast, doesn't it? Now translate each one into fundamental units. The period is a time. Both masses are, well, mass. And the distance is a length. Three basic dimensions in play: mass, length, and time. And here's where it falls apart. Look closely. Length shows up in only one place, the distance r. And time shows up in only one place, the period. To cancel a dimension that appears just once, you have no choice but to throw that quantity away entirely. So out goes r. And out goes the period. What are we left with? Just two masses. And the only dimensionless thing you can build from two masses is their ratio. Which would mean the ratio of the two masses is always some fixed constant. The same for every pair of planets in the universe. That's obviously nonsense. So something's missing. The thing we forgot is a constant of nature. Newton's gravitational constant, g, is universal, the same everywhere in the cosmos. But here's the crucial part. G is not dimensionless. And that's exactly why it can save us. Where do its units come from? From Newton's law of gravity itself. Force equals g times the two masses divided by the distance squared. Rearrange for g, feed in the units, and out comes something beautiful. Length cubed, per mass, per time squared. G carries mass, length, and time all at once. That's the link the list was missing. Now we rebuild, canceling one dimension at a time. First, let's kill the time. The period has one power of time. And the square root of g carries a stray 1 over time. Multiply them together, and the time vanishes completely. What remains is the square root of length cubed over mass. Next, the length. We've got length cubed hanging around, and the distance r is pure length. So divide by r to the 3/2, the square root of r cubed. And the length disappears too. Now only mass is left. Last one, the mass. We've still got a stray 1 over the square root of mass. So multiply by the square root of one of the masses, u2, and even that cancels. Now the whole thing is finally dimensionless. Every unit, gone. Here's the payoff. The left side has no units. So the right side can't have any either. It can only depend on things that are already dimensionless. And the one dimensionless thing left is the ratio of the two masses. So this group has to equal some function of u1 over u2. Now just solve for the period. It equals the square root of r cubed over g times u2 times that function of the mass ratio. And when one body dwarfs the other, the Sun against a tiny planet, that function is basically a constant. So the period squared is proportional to r cubed. Kepler's third law. Exactly. So that's the quiet lesson. Dimensional analysis handed us the exact shape of Kepler's law, the constant out front. Experiment still has to measure just like Kepler did. But the real gift was the failure in the middle. When the units refused to cancel, they weren't wrong. They were whispering that a piece was missing. Sometimes a dead end is the best clue you'll get.